Good evening, everyone. My name is Aditya Sharma, and this is aircraft propulsion course being conducted by Department of Mechanical Engineering, IIT Guwahati, under the NPTEL program. And we are into the seventh week of this course, aircraft propulsion. Related to each week, we are conducting one live tutorial session. This is one such session. So till now we have conducted six such sessions, and the recordings of all these sessions can be found on the course page on the Swam portal. So basically, these are YouTube links. And the instructor for the course is Professor Vinayak Kulkarni. He is affiliated to Department of Mechanical Engineering here only at IIT Guwahati. And I am also a research scholar uh, at Department of Mechanical Engineering, IIT Guwahati. So, theme for today's discussion and questions is aircraft engines and their examples. So, before I start, just wait for a couple of minutes. After that, I'll start the session. Thank you. So we can start with the session. So theme of today's topics discussion is aircraft engines and their examples. Total three lectures are there in this week's content. Lecture number 20 to lecture number 22. In these lectures, three engines, three different types of engines have been discussed. First one is your turbojet engine, second is your turbofan engine, and then is your ramjet engine. Previously, also we have been introduced to these engines in this course. Okay. Okay. We shall see again these engines and discussion on them. Then we'll take questions related to each lecture. So turbojet engine, turbofan engine, ramjet engine. Then so all these are non-reciprocating type of engines. So first we'll see topics. So this we have been doing in previous sessions also. So lectures related, topics related to lecture 20, then questions related to it, then related to lecture 21 topics, then questions related to it, then lecture 20 topics related to it, and then questions related to it if we have. Okay. So first lecture is lecture number 20, turbojet engine. Its configuration has been discussed and then examples have been discussed. So in this content, lecture 20 is content, I'll just discuss the configuration of turbojet engine and then we shall see questions related to it. Okay. The two numerical questions have been discussed in this lecture. Okay. So turbojet engine in that case. So schematic has been drawn and I will draw the schematic only. So we have intake, first of all, different sections, different parts of these engines, be it intake, compressor, combustion chamber, turbine. So Even nozzle we have discussed recently. Intake and nozzles was the last week's content, right? So this is intake, and then after intake, we compress the working fluid. So our cycle works on working fluid works on Brayton cycle. In case of aircraft engines or turbojet engines or jet engines. To add combustion chamber, there will be heat addition. Then there will be expansion of the gases that we have obtained from the combustion of fuel and combustion chamber. So expansion will take place at our turbine, and then again we accelerate it, the gases using nozzle, and then the gases will exit from the exit of nozzle. So initially we have this mass flow rate of fluid, which is moving with velocity CA, and the pressure here is PA. Okay. Then there are efficiencies involved with each component. So for intake, we have seen this that we call RAM effect, right? If I remember it correctly. And then this is isentropic efficiency of your compressor, and this is efficiency related to your combustion. Then you have isentropic efficiency of your turbine. Then this is of nozzle that we have recently seen. Then at the exit, we have velocity of jet and the pressure here, PJ. Okay. So these things we have. Then there is efficiency of transmission. Because we know that our compressor is being run by our turbine. Okay. So the transmission of work from turbine to compressor, it will have losses. And numerically, if we have to see it in terms of this eta TR, that is efficiency, transmission efficiency. Okay. Then expression for thrust has been given, which is mass flow rate of air plus mass flow rate of fuel. So this also we have seen previously. Okay. So this is because of your jet velocity part, and this is because of your pressure at the exit and inlet. Right? AJ is the area of the exit section of the nozzle. and compressor work is 9 pr. Or you can write it as like this. Right. So this is about your turbojet engine. Then there are questions, two numerical questions that have been discussed in lecture number 20. And for us, discussion on turbojet engine is up to this point only. And now we will see the questions. So I have a question. In front of you here. Please read this question first. Let's see the options and try to see which option you believe is correct and why. And if you have some answer, you can give it in the comment box. Else we will discuss it shortly. So the question here says that consider the following components that are typically used in a turbojet engine configuration. First is your turbine, then is your diffuser, then is your compressor, then is your propelling nozzle, then is your combustor. So we have been given components of a turbojet engine. Turbine, diffuser, compressor, propelling nozzle, and combustor, and which of these are non-rotating components? Then, is turbine a non-rotating component? No, turbine is a rotating component. Is diffuser a non-rotating component? Yes, diffuser is a non-rotating component. There is no rotation as such here. Okay. In the intake section, you have seen this. Okay. Then compressor is a non-rotating. No, compressor is a rotating. Both turbine and both turbine and compressor are rotating components. Then Propelling nozzle is rotating, propelling nozzle is not non-rotating. Is combustor your non-rotating? Yes, combustor is non-rotating. No rotating component in combustor. So second, fourth, and fifth. You see the options. Option D comes out to be the correct option. Okay, so D is the correct answer to this question. Then we'll move on to next question. So some data has been given. So we'll just jot this down. It's given in 2 pages, 2 slides data. First, have a look at this data. So question talks about a turbojet engine. Let's read the question first, paragraph first, and then based on this paragraph, we'll do the questions. So the paragraph goes like this: the component performance parameters for a turbojet engine flying at a speed equivalent to Mach 0.7 and an altitude of Mach 0.7 and an altitude of 9,000 meters are as follows. Component performance parameters. So components like turbine, compressor, okay, intake, nozzle. Okay. So first of all, pressure ratio has been given for compressor, for a compressor, that is 7.0. Then turbine inlet temperature is given, which also is the exit of the combustion chamber. That is also the maximum temperature involved in your Brayton cycle. Then isentropic efficiency of compressor is given as 0.82. Isentropic efficiency of turbine is given as 0.89. Then isentropic efficiency of intake is given as 0.92. Then isentropic efficiency of propelling nozzle is given as 0.93. Then transmission efficiency that we are saying beta TR is 0.99. Then combustion pressure loss is 2.5% of the combustion delivery pressure. So we have seen this. If you remember, if this is your in your TS diagram, if this is your compressor, then this is your goes like this. Okay. From here with combustion, you have pressure loss. Okay. Here we have the turbine, combustion chamber, compressor. Here this is P02, this is P03. So this 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 basically is 3.5% of combustion delivery pressure. Okay. Then fuel to air ratio is given 0.0176. F by A, fuel to air ratio is given this. Then universal gas constant R is given as 287. Then at 9,000 meter altitude, you have been given pressure as this, temperature as this, speed of sound as this. Okay. Their static properties, static values. And then for air, your specific heat and constant pressure is this. Gamma is 1.4. For your gas, after combustion of your fuel and air mixture, the gas will have this specific heat and its specific heat ratio is this. Okay. So all this is given to us. So we'll just first of all jot this down and then we'll questions based on this. Question number 7. Pressure ratio, compressor pressure ratio is 7. Maximum temperature is T03 is. So I'll just draw the diagram again here. Before that, I'll just draw down what has been given here. Then I think efficiency of compressor is 0.82. Then of your turbine is 0.89. Then of intake is 0.92. For nozzle efficiency is 0.93. Transmission efficiency is this. And fuel to air ratio is given as this. This. Then for air at 9,000 meter altitude, for air you have CPA equals to 0.005 joule per kg Kelvin. Then gamma A is equal to 1.4. For gas, EPG is 1.147 kilojoule per kg Kelvin. Gamma G is 1.33. And at 9,000 meter altitude is this. Temperature is 229.7 Kelvin. Then speed of sound is 393.7 meter per second. So we'll draw the diagram first of all. Find the diagram. We'll just take questions. So this is for a compressor. This is P2. Okay, this is 3, and this is P3 pressure. This is not flowed. This is real. And for here, we are taking the static conditions, right? So this is your PS diagram for the question. Right? Then, so this is your compressor, combustion chamber, turbine. Okay. Then we'll see the question. Real total temperature at the exit of compressor. We have to see. We will solve it. Real total temperature basically is T02. So we'll work with compressor first of all. Solution for compressor. And in that, what happens is total temperature is Ta plus Ca square by 2 Cpa. Here Pa we have, Cpa we have, C initial velocity we don't have. See what is given to you. But it is given to you that Mach is 0.7. Yes, the first line of the paragraph it is given that Mach is 0.7. So now Mach is Ca by A, implies Ca is Mach into A, 0.7 into A. A is given as 303.7 at 9,000 meters. Okay. Now, if you work this out, this is 212.59 meters per second. Okay. So this is T01. This is M. Okay. Yeah. Let's see. Where is T01 equal to is 229.7 plus 212.59 square divided by 2, or it's in kilojoules per kg Kelvin. So we'll convert it to joules per kg Kelvin. So for that, we'll multiply it with 1000. Now, if you work this out, this will come out to be 252.18 Kelvin, right? Now, why we are doing all this? Because eventually, what we want is we want T naught 2, and for T naught, the formula is this P naught 2 by P naught 1 gamma minus A by gamma minus 1. Not draw this. But we want this. Okay. So in this formula, we have this. Okay, we just found out this. So this can be used here. Then we need to find out if this will suffice. Okay. If we place this 252.18 plus 252.18 divided by efficiency of compressor is 0.82. Then this ratio P naught 2 by P naught 1 is basically pressure ratio of compressor. This is 7. Then gamma is 1.4. So this will become this, right? Right. This. If you work this out, this will come out to be 480.87 Kelvin. So this is the total temperature at the exit of compressor. Okay. So this was question number 2, 480.87. Then next question is total pressure at the exit of turbine. total pressure at the exit of the turbine has been asked. If you see the diagram, at the exit of turbine is P04. So this pressure has been asked. P04 we need to find out. Now to find out P04, question number 3, solution. So we want P04. So P04 is equal to P04 by P03. You can write it like this. And then P04 by P03 can write as this. G by economic G minus 1. Okay. Please note that here the ratio of specific heats has been given for gas and not air. Now here we need to find out P04. Okay. P03 is given in the question, that is 1100 Kelvin. P03 also we need to find out. So for finding out P03, formula is P03 is equal to P02 into P03 by P02. Okay. Yes. This also can be written as P02 minus P03 by P03. PB by P02. This can be written this way. P02 into this becomes 1 minus delta PB by P02. Now, do we know P02? If you see, P02 is not given anywhere. Okay? You need to calculate this. Same way for P02. P02 is equal to P02 into P01 by P01. For this, we know what is this. This is 7. Okay. P01 is have we calculated P01? We have not calculated P01 yet. We will calculate P01 also. So now to calculate for P01, P01 by PA. This is the formula 1 plus intake CA square, that is inlet velocity, by 2 CPA PA. Okay. Gamma A by gamma A minus 1. This is the formula. Now if you place the values here, 0.92 to 12.59 squared divided by 2 into 1005 into 229.793. 229.7. So this is this, this is this, this is this. The whole is 1.4 by 0.4. Now implies P naught 1 by PA is equal to this. So if you work this out, I have calculated this to be this much. If there is some mistake in the calculation, please write in the comment box. Then PA we have 1.3522 into this comes out to be 0.4165 bar. So P naught 1 we have now. Okay. So implies P naught 2 is equal to 7.0 into 0.4165. So this will come out to be 2.9155 bar. So then P naught 2 also we found out. Then P naught 2 we have, P naught 1 we have, and we can find out P naught 3. So P naught 3 we found out from here. So implies P naught equal to P naught 2, that is 2.9155 into 1 minus. So delta PB by P naught 2 is given as 3%, that is 0.035. So if you calculate this, this will be 2.8134. Right? So P naught 3 we have now. Now we want to calculate T naught 3. Right? This we have. This we have. Now we want T naught 4. T naught 3 we have, we want T naught 4. So for turbine at outlet T naught 4, this ideal one is equal to T naught 3 minus TTA T naught 2 minus T naught 1 CTG and PR. Right? In terms of transmission efficiency, this has been given. Now if you place the values, So this will come out to be this. Then from here you can calculate T naught 4 because you want to calculate T naught 4. So for T naught 4 formula is this from turbine efficiency, from the definition of turbine efficiency, you can calculate. This is so if you calculate this, this will come out to be this much. Okay. Then we have now T naught 4. So T naught 4 is equal to, because P naught 4 is this, P naught 3 is 2.8134. T naught 4 is 872.57. T naught 3 is 1100. Gamma G is 1.33 divided by 0.3. So if we calculate this will come out to be around 1.1061 up to decimal points. Then so this is the answer to question number 3. Total pressure at the exit of turbine is 1.1. I hope this is clear. This was a bit lengthy question. Here for P naught 4, we for the exit pressure at the turbine, we needed two values. First was of P naught 3 and then second was of P naught 4. So first we calculated P naught 4, P naught 3. So for P naught 3, we then realized that we need to calculate value of P naught 2 and P naught 1. From calculating P naught 2 and P naught 1, we calculated P naught 3. Then once we have P naught 3, now we want to calculate P naught 4. P naught 4. Okay. So for calculating T naught 4, first we calculated T naught 4 dash. And because T naught 4 dash can be used in this formula of T naught 4 related to turbine efficiency. From here we calculated T naught 4. Now we have T naught 4 and T naught 3 and we can calculate P naught. So this is question 2. So next question is critical nozzle pressure ratio is. What is critical pressure ratio, nozzle pressure ratio? We have seen in the previous week's content that if your pressure falls below this while expansion, so in that case your nozzle is choked. Okay. PC, critical nozzle pressure, but pressure ratio is P04 by P. Critical nozzle pressure ratio is P04 by PC, which is equal to 1 by 1 minus 1 by heat of nozzle, then gamma G minus 1 by gamma G plus 1 raised to power gamma G by gamma G minus 1. Okay. So if you place the values here, nozzle efficiency is 0.93. Gamma G is 1.33, so this is 1.33 divided by 1.33. This is 1.33 divided by 0.33. This will come out to be 1.94. So this is basically the answer. And now if your by P5 is greater than P0 by PC, in that case, your nozzle is choked. In that case, your nozzle is choked. It's scheduled KUB. So answer is 1.94. So whether this is choked or not, you can see this from nozzle pressure ratio. If you see P04 by PA, because P5 and A are same, so this is 1.1061 divided by 0.3083. See this? So this is 3.5912, which is clearly greater than 1.94. In that case, your nozzle is choked. Now flow velocity at the nozzle outlet. We need to calculate. So it's just C5. Question number 5. So C5 basically is this. Here we need to find out TC. So T5 is equal to TC is equal to okay. So this is 3.2.33 and 1404 is 897.59. Now if you work this out, this will be 770.46 Kelvin. So this is your temperature T5. So we are doing this numerical based on turbojet engine. Okay, where we are trying to find out the flow velocity at the nozzle outlet. Okay. So this basically is the question for which we have been given some data. So till now on this paragraph, we have found out the race. Sandhya, you want to ask something? Your mic is unmuted. You want to say something? You can. Otherwise, okay. So then we found out, first we found out the total temperature at the exit of compressor, then the total pressure at the exit of turbine, then we saw critical nozzle pressure. Now we are seeing the flow velocity. Now to find out the flow velocity, I have just calculated T5. Based on this formula, we will calculate our flow velocity at the nozzle outlet. So T5 is this. Then implies C5 is equal to 1.33 into 287 into 770.46. If you calculate this, this will come out to be this looks right. This basically is your C5. Then specific thrust we need to find out of the nozzle. So to find out the specific thrust, what we will do is question number 6, if you see, specific thrust Fs equal to C5 minus Ca plus A5 by mass flow rate. Then Pc minus Vk. Okay. So here first we have this, we have this, right? We have this, but we don't have this. So to calculate this will be this, right? And to find this out, just place the values. Now have we calculated row 5? So row 5 we have not calculated yet, I believe. So to calculate row 5 basically is PC by R PC. Okay. P is equal to rho RT using this formula. PC we have just PC we don't have. So just calculate PC also. This we want, this we have. right? So PC is equal to P5 is equal to 1 by P04 by PC, P04. Yes, Sandhya. Please, please ask. You have raised your hand, please ask. I'm waiting. Sandhya, you have raised your hand, please ask. Or you can just type your query in the chat box. Yes. Uh, what part you did not understand? Oh, the PC value. So this basically is this. So I'm writing P5, right? So what I'm doing is I'm just writing is it like this. PC. This you understood, right? P5 is PC. So what I'm doing is I'm multiplying it with P04 and I'm dividing it with P04. This is what I'm doing. Right? Now to this thing, now to this thing, what I'm doing is this whole thing, what I'm doing is I'm writing it as 1 by P04 by PC. This is what I'm doing. Nothing special. This is what I have written just. I hope this is clear. Yes. And this we have already calculated. Okay. So this we have already calculated somewhere here. With P naught A by PC we have calculated as 1.94. So 1 divided by 1.94 P naught 4 also we have calculated. So if we calculate this will come out to be this much. I hope this is clear. All right. Then now we have PC, then row 5 we can calculate. Row 5 is PC 0.5701. Because this is in bar, we will convert it into pascals. Then in denominator RTC, R is 287, TC is 770.46 Kelvin. So TC we have calculated. Okay. TC we have calculated in the previous question. Here 770.46 Kelvin. Right. So row 5, this becomes 0.2578 kg per meter cube. So this becomes this. So this is your row 5. Then specific, because the question asks specific thrust, and in specific thrust we needed this, and for this we needed this, right? Then we can now find out. So implies this ratio is 1 divided by rho 5 C5, 1 divided by 0.2578, 2578 into 542.30. Okay. So if you work this out, if you calculate this, this will come out to be this. So this is C5 is 542.30 minus CA is 212.59 plus A 5 by M is 0.0071 into this pressure is PC 0.3080 minus 0.5701 minus 0.2080, right? So because this is in bar, so convert it to Pascal. Now if you work this out, this will come out to be 515.80 second per kg. This basically is your specific thrust. Then specific fuel consumption. Next question is, so this is specific thrust 542 to 515.80 Newton second per kg. Question number 6 and question number 7 is specific fuel consumption. So specific fuel consumption is fuel to air ratio divided by specific thrust. Fuel to air is 0.0176 divided by 515.80. To calculate this, this has been converted. If you see this here, the question asks in not in second but R, right? R per R Newton. This has been converted into per R Newton, right? by multiplying with 3600. This is your specific field dimension. This question. Then we are done with this question number 20. Now we want turbofan engine and ramjet engine. These two topics are left. So let's see these. Before starting this, let's take a small 5 minutes break and then we can continue the session. Okay, the next lecture is turbofan engine. So turbofan engine's configuration has been discussed and then examples. One example has been discussed. So this is turbofan engine. So its configuration is like this. In front, if you ever sit in a commercial aircraft having a turbofan engine, you'll see in front of this engine. So you have two engines on the left and right hand side. usually below the wings. Okay, so the front of the engine you see, that is basically the fan part, from where your air enters into your engine. Then some section of this air is bypassed. That is, it will not pass through your compressor, your combustion chamber. Okay. And for this, we will have a bypass ratio also. Then uh, this is the bypass of your uh, turbofan engine. Two types of nozzles. One is a hot nozzle for your products from your combustion chamber, right? From the main engine, the combustion chamber, your turbine, and from turbine to your nozzle. Then is your bypass nozzle, which is also called cold nozzle or fan nozzle. So this, in simple words, is air coming in and air going out with some nozzle at that. Okay? So this is the basically configuration of a turbofan engine. So mass flow rate, the whole mass flow rate is mass flow rate of cold plus mass flow rate of hot working fluid, right? And then bypass ratio B is equal to mass flow rate of C by mass flow rate of H, right? So this is a turbofan engine. Then questions based on this. So in a twin spool turbofan engine, the fan is driven by four options have been given. Whether this is low pressure turbine, high pressure turbine, high pressure compressor, external power sources. So in a twin spool turbofan engine, fan is driven by, first of all, it will be driven by some turbine. This turbines only drive your compressors and your fan also. And in your turbofan engine, your fan is driven by two options are A or B. So out of this, A option is correct. Okay. So this is fan is driven by a low pressure turbine. Then question number 9 is choose the correct path of air from the inlet to the outlet of hot nozzle in turbofan engine. To inlet to outlet, you have to choose the correct path for air. So we have seen this fan, but no, this is not right. Fan, compressor, this is right. Then it says turbine. No, this is not right. How can turbine be before combustion chamber? This is not right. The third is fan, compressor, combustion chamber, high pressure turbine, low pressure turbine, nozzle. This seems right. Fourth is fan, combustion chamber. Again, how can combustion chamber come after fan? This is not right. So C is the correct option. Right? So C is the correct option. Then moving on to next. So lecture number 22. So next slide is lecture number 22. So lecture number 22 is based on ramjet engine parameters and losses. So in ramjet engine, what I'll discuss parameters and losses. Okay. So this is ideal ramjet engine cycle, then expression for thrust and specific fuel consumption, then effects of losses in ramjet. So I'll discuss this first. This you can see from your lecture. Then effect of losses in ramjet engine. Because this has diagrams, so I can discuss diagrams. So first and third topic. Lecture number 22. This topic is ideal ramjet engine cycle. It is something like this. Then we have this cone and structure for inlet purpose and to compress the air coming in. So in ramjet engine, you don't have a compressor as such separately. So this acts as intake. Then this acts as burner. Where combustion takes place of your fuel and air mixture, and then nozzle accumulates. And if you draw the TS diagram, it is like this. this is your intake. This is your burner. This is your nozzle. Okay. So the reason for skipping three basically is that here expansion is not taking place in turbine, right? So if you see the turbojet engines diagram, so expansion that takes place in turbine. So in the example, we have drawn this. If you see this, so this 3 to 4 is not there in Ramjet. If you compare the turbojet with Ramjet or Ramjet with turbojet, 3 to 4 is not there. So, but the numbering we have kept the same just for the comparison. This has been done in the lecture this way, so okay. The expansion of the nozzle is from 4 to 5, so this has been kept like that only. So this basically is the TS diagram for your ramjet. Then effects of losses in ramjet engine. So loss in ramjet engine. This is not 4 again, not 5, 5, 8. So here, if you see this loss is pressure loss, is with intake. This is with your burner, like was in your combustion chamber. Right? And this is with your block. So this basically is the real scenario in case of ramjet engine. Then some ratios have been given. First is your diffuser stagnation pressure. ignition pressure ratio RD, which is P02 by P0A. Okay, so this and this. P02 is less than P0A. Then is combustion chamber. Ignition pressure ratio, which is equal to P04 by P02. This also P04 is less than P02. Then third is nozzle pressure ratio, which is equal to P05 by P04. Right? Here also P05 is less than P04. So these are your this is your real case scenario for your ramjet engine with losses. Okay. So we don't have a compressor here in this ramjet engine. This we have to remove. And this is used at supersonic speeds. Okay. So effects of losses, pressure losses that are shown by PS diagram. For Ramjet engine, then we can see question. So Ramjet engine is used for your at supersonic speeds, right? But then the combustion has to be at the subsonic speed. Okay. So question number 10, for a given Mach number, the specific fuel consumption of Ramjet engine increases with maximum engine temperature, decreases with maximum engine temperature, initially increases and then decreases with maximum temperature. Doesn't change with maximum engine temperature. So 4 options have been given. This is question number 10. So what happens to your specific fuel consumption? So specific fuel consumption, if you see your lecture number 22, find one diagram there, something with SFC. This basically says that with increase in your maximum engine temperature, that is T04, your SFC increases for same Mach number. This one will be higher than this one. When T0 over in this case is greater than T04 in this case. T04 in first case is greater than T04 in second case. So A option is the correct option in this case. Then question number 11. In the case of a ramjet engine, air enters from the intake at dash speed and encounters combustion at the combustion chamber. So it enters at supersonic speed and the combustion takes place at subsonic speed. So C is the correct option. Right. So this is it about today's session. So today's session was on aircraft engines, 3 types of. So I'm concluding today's session in that case, because we have come to the end of this session. So I'll conclude in that case. So this session was on aircraft engines and their examples. So 3 types of engines have been discussed. One is your turbojet engine, then turbofan engine and turbo ramjet engine. So configurations of these three engines have been discussed, drawn. Okay. The turbojet engine and turbofan engine, you use compressors explicitly, but in your ramjet engine, you don't use the compressor explicitly, rather a cone by means of shock compresses the air. Then we saw numerical, around 6 numericals based on a turbojet engine from question number 2 to 7. Then we saw a few questions on turbofan engine. Right? So in turbofan engine, you have some air is bypassed and then some air enters the main core of the engine. Then you're in ramjet engine, you don't have any compressor that I have just said, and then it is used at supersonic speeds, but the combustion in the engine takes place at subsonic speed. This is it about your session number 7 of aircraft propulsion course. So thanks for watching this session. The next session will be on coming Tuesday again with the same timing, 6 to 8 p.m. Well done. Thanks for watching.